Window shading is an important means of building's heat protection. Through window shading, it can prevent indoor overheating, glare, and deterioration of objects. The design requirements for window shades are: first, the shading structure can prevent sunlight from irradiating the room in summer and does not affect the use of solar radiation for heat preservation in summer. Second, when it is sunny, it can block direct sunlight from entering the room, and when it is cloudy, it can ensure that the room uses natural lighting to meet the illumination standard. Third, minimize the heat shield effect of the sunshade structure, preferably to get the heat into the room. Fourth, the sunshade is also used as a rainproof component, and the ventilation cannot be affected in rainy days. Fifth, cannot block the view from the outside. Sixth, the structure should be simple, economical, and durable, and be in harmony with the architectural shape. According to the shading position, the shading forms can be divided into 5 types: glass self-shading, external shading, internal shading, intermediate shading, and green shading. Among them, the glass's own shading is realized by the blocking ability of glass itself to solar radiation. Surface treatment or adding raw materials in the production to improve the blocking ability can be made of heat-absorbing glass, heat-reflecting glass, low-E glass, etc. The intermediate sunshade is a built-in lower in the middle of the insulation glass, which can be opened and closed by light control or thermal control. What is the difference in the shading effect of these different forms of shading? Let's first compare the self-shading effects of the 3 types of glass. Ordinary glass has a greater amount of transmitted radiation, 86.5%. After adding the amount of solar radiation entering the room by convection after the glass absorbs solar radiation, there is a total of 88.9%. The amount of radiation absorbed by the heat-absorbing glass is large, which is 46%. After the glass heats up, the proportion of convection scattered to the outside also increases. So light, the amount of solar radiation that finally enters the room is reduced to 60%. The amount of reflected radiation from heat-reflective glass is larger at 38%. The amount of absorbed radiation is also larger at 32%, which reduces the amount of solar radiation that eventually enters the room to 40%. Think about it. Is it feasible to choose the glass form based on the maximum amount of solar radiation entering the room? Combined with architectural design work, what kind of thermal impact will the heat-reflective glass bring to the surrounding environment? Combined with the behavior of opening window glass, and various forms of shading structure can be combined to form a variety of use cases. Let's take a look at another figure, which compares the solar radiation heat entering the room under 5 different conditions. In the Fig A, there is no sunshine when the window is opened, and all the solar radiation enters the room. Picture B shows the opening of the window and the inner curtain. The solar radiation scattered to the outside accounts for 70%. Part of which is reflected by the curtain, and part of it is absorbed by the curtain and then convection out. The solar radiation entering the room accounts for 13%. Part of which is transmitted through the curtain, and part of it is absorbed by the curtain and enters by convection. Picture C shows the window closed and the glass is used to shade itself. The solar radiation scattered to the outdoor accounts for 19%. Part of which is reflected by the glass, and part of it is absorbed by the glass and then convected out. The solar radiation entering the room accounts for 81%, of which the transmitted radiation accounts for 77%, and 4% is absorbed by the glass and convection into the room. Fig D is the closed window and the inner blinds. The solar radiation scattered to the outside accounts for 49%. Part of which is reflected by glass and lowers, and part of which is absorbed by glass and lowers and then convected out. The solar radiation entering the room accounts for 51%, which is reduced by 30% compared to the fig C, part of which is transmitted by the glass and the lowers, and part of which is absorbed by the glass and the lowers and convection into the room. Fig A is the closed window and the outside blinds. The solar radiation scattered to the outside accounts for 82%, part of which is reflected by glass and lowers, and the part is absorbed by glass and lowers and then convection out. The solar radiation entering the room accounts for 18%, which is reduced by 33% compared with the fig D, part of which is transmitted by the glass and the lowers, the part of which is absorbed by the glass and the lowers and the convection into the room. It can be seen that the effect of external shading is better than that of internal shading. Basic forms of external sunshade are horizontal, vertical, integrated, and bevel. The horizontal type is suitable for south-facing windows or north-facing windows in low-altitude areas because it can block sunlight with large solar elevation angle projected above the window. The vertical type can block the sunlight with large solar elevation angle obliquely projected from the window side, so it is suitable for northeast, north, and northwest windows. The integrated type can block the sunlight with medium solar elevation angle obliquely projected from the front of the window, so it is suitable for the windows near the southeast or southwest direction. The bevel can block the sunlight with small solar elevation angle facing window, so it is suitable for the windows near the east and west directions. This picture shows the applicable origination of different shading structure, and the different shading forms can be selected according to the origination of the window. Shading effect of the shading facility is expressed by the shading coefficient. The shading coefficient refers to the ratio of the amount of solar radiation that penetrates into the window with shading and the amount of solar radiation that penetrates into the window without shading during the irradiation time. A small shading coefficient means that the amount of the solar radiation penetrated is small and the heat protection effect is good. External shading is represented by the external shading coefficient SD, that is, the ratio of amount of solar radiation QS that penetrates into the window with external shading to the amount of solar radiation QN that penetrates into the window without external shading. This value can be used to analyze the influence of external shading on building energy consumption. The external shading coefficient is related to the shading structure size ratio, which can be calculated by a simplified formula with the shading structure size ratio as a parameter. The external shading coefficient is related to the material, and the external shading coefficient needs to be corrected when the light transmitting material is used. The external shading coefficient of the integrated type is equal to the product of each external shading coefficient participating in the combination. For example, the external shading coefficient of the horizontal and vertical combination is equal to the horizontal external shading coefficient multiplied by the vertical external shading coefficient. The shading effect of the glass itself expressed by the coefficient SC, which refers to the ratio of the amount of solar radiation actually passing through the window glass to the amount of solar radiation passing through the standard transparent glass with a thickness of 3 mm. Then the prehensive shading coefficient is equal to the glass itself shading coefficient SC multiplied by the external shading coefficient SD. Shading has a certain impact on ventilation and natural heating. The indoor wind speed is reduced by about from 22 to 47%, and the indoor illuminance is reduced by about from 53 to 73%. In order to prevent the hot air raging due to the heat absorption of sun weather from entering the room and reduce the impact on ventilation and lighting, the solid sun weather surface of the middle floor can be designed in form of louvers or some louvers near the window. According to the figure A and B, you can also install a sun visor at a certain distance from the wall or add heat-absorbing glass in front of the sun visor, according to figure C, to enhance the shading effect. The size of the shading component needs to be determined by calculation. The calculation of the forward extension lines and the side extension lines of the horizontal plane is similar. The difference is the calculation of the difference between the solar azimuth engine and the wall azimuth engine. The former adapts the cosine and the latter adopts the sine. The calculation of solar altitude engine and solar azimuth engine is learned in the next chapter. The wall azimuth engine refers to the engine between the normal line of the wall surface and the source direction. Slabs only need to calculate the forward lines. The forward lines of vertical and horizontal planes should be calculated respectively for the comprehensive sunset plane. The wall thickness should be deduced. For the baffle type, the size of each component should be calculated, including the forward extension lines and the side extension lines of the horizontal plane and the raised height of the vertical plane. Next, let's do an exercise. To design a shading board for a north window of a building in Guangzhou, it is required to shade the sunlight at 3 p.m. in mid-October. It is known that the window width is 1.5 meter, the window height is 2 meter, the wall thickness is 24 centimeter, and the north latitude is 23 degrees. Since the design requirements of the sunset plant need to determine the size and form, the solution to this problem is: first, the horizontal shading is selected according to the orientation of the window, and the forward and lateral extension lines of the horizontal plant are calculated. Secondly, the feasibility analysis of the calculation results is carried out, and when the shading conditions are not met, the comprehensive formula is replaced. Then, the wall thickness as part of the sunset board size to be corrected. Finally, according to the above calculation results and the climatic characteristics of the region where the building is located, the sunset plane form is determined. First, according to the given geographical latitude, date and time, the solar latitude angle is calculated to be 37 degrees, and the solar azimuth angle is 63 degrees. According to the given conditions, the wall azimuth is 0 degrees, and the difference between the solar azimuth and the wall azimuth is 63 degrees. Set the horizontal plane to the upper edge of the window, and then H takes 2. Substituting into the formula, the forward extension lines of the horizontal plane is 1.2 meter, and the side extension lines is 2.36 meter. The wing plate with a length of 2.36 meter is suitable for continuous windows, but it is not suitable for a single window. Therefore, the horizontal formula is changed to a comprehensive formula, and the forward extension lines of the vertical plane is 0.76 meter. Since the above size is calculated from the outer surface of the external wall, considering the wall thickness, the actual extension lines of the horizontal plane is 0.96 meter, and the actual extension lines of the vertical plane is 0.52 meter. Next, determine the shading form. Since Guangzhou is a hot summer and warm winter area, it can choose fixed or active sunset, and the solar elevation angle changes day by day, so the effect of choosing active sunset is better than little fixed sunset. Therefore, the active sunset is determined. Lightweight materials should be used to reduce the weight of the sunset plant, and the absorption coefficient of solar radiation on the inner and outer surface should be small. Light-colored bright paint should be applied on the sunny side to strengthen the reflection of the surface, but dark, non-gloss paint should be applied on the opposite side to avoid the reflection sunlight into the room. At this point, this problem is all completed. Please try the seating design in combination with the architectural design work. You can also think about how the seating design can be integrated with the building. What architectural scale can be expressed with sun wedges? What high-tech technologies can the sun wedge be combined with to achieve near-zero energy consumption? How are fixed sun wedges applied to prefabricated buildings?